this one and this one. This is what you said, 2-piece test. So they are both in the same family. Okay, and these are called range tests. So what does it mean? It basically is that, again, let's take an example of this 4 groups. We have 4 means, and let's assume just for argument's sake that this mean is the lowest. So this is the highest mean value, and this is the lowest mean value. It doesn't have to be group 1 has to be always lowest, but it doesn't matter. But rank order, let's say we rank order the means. Right? So you begin comparing the highest to lowest. That's what the range word comes from. Alright. So F test is done. You found a difference. That's the first part is done. Now you come and you just use, I'm going to compare this to this. Using the same idea of t-test concept, so that it will be x1 bar minus x2 bar over standard x1 minus x2. The same thing. This comes from standard. This is the analysis of variance gives you these values. So
here you don't adjust that divided by.
No.
Yeah. Just straight t-test.
Well, no. The variance estimation comes from analysis of variance. So there you are taking into account everything together. It's not based on just those 2 groups. It's based on all groups. The variability within the group is a net variability assessment based on all groups.
Okay.
That's the difference. So basically, but the idea is still the same. The mean difference and some variability index at the bottom. That's the idea. So you go ahead and you do this, right? And if you find a difference and you look up, it computes a quantity called Q. And there's a Q table. So Q tables depend on what? They depend on the number of observation, of course, just like t-test, but also they depend on the number of means span. That's what they call it. So here in this example, 1, 2, 3, 4 means are spanned. So if you look up any of the Newman School Q tables, they call any of the books would have it. That's another variable available. So it's just like t-test. In t-test, only thing variable over degrees of freedom is all you need for t-test. Here is degrees of freedom, which is the number of observations, related number of observations, and there's another called number of mean span. So if you had 6 in here, in the very first it will be 6 span, and so you'll see how that critical value changes with that. So if you found a difference there, then that's done. Then you say, okay, that's step number 1. Second step, then the highest. So this is so the lowest to the highest, then the lowest to the next highest. This is second comparison. Using the same. Now it will be x1 minus x3, and the same on the denominator. But the Q factor would be 3 here. And so you look up the table, the difference. Let's say you found a difference, okay, that's done. Let's say you found a difference, that's okay. Then you go x1 minus x2, maybe you didn't find a difference. Then you start with this one, and you go with this, and so forth. Now, the only last point is, let's say you found a difference here, right? Let's say you did not find a difference here. You stop, in the sense, you do not go inside anymore. You cannot do this anymore. Let's say you stop. You go now this way. And let's say you didn't find a difference here, no more comparisons here. So whenever you fail to find a difference, that span, you don't go further anymore. And so this is what sort of, it preserves some logical consistencies. That, oh, there was no difference here, but there's a difference here. It can't be. And it's logically inconsistent. That these 2 groups are not different, but these 2 are. It doesn't make sense, because they're on rank order. Right? So that's sort of the gist of this Newman-Coos. And the 2 key is exactly related to Newman-Coos. All it does is that here you see how the factors spanning the number. Here to here comparison, there are 4 mean span, whereas here to here there are 3 mean span. As the number goes down, the requirement of the critical value becomes less and less. But what Tukey does, he says, oh no, I'm going to keep always. There are 4 groups. It's always going to be 4, no matter whether I'm doing here, so it becomes a little more conservative. But it's exactly the same thing. All right. So these are the 2 most popular, SNK or Tukey are the most popular ones. Within them, this is more conservative. Overall, this has a good balance between being liberal and conservative. So neither one of them are as conservative as Bonferroni. Because Bonferroni is the most conservative. Just because you're really cutting, making that critical value so low, the T instead of 0.05.
So Newman-Cool's is the most liberal one.
These are both range tests using this concept of range. Between those two, this is more conservative, this is more liberal.
And Home and Bonferroni, they're much more stringent.
Yeah. So in the pecking order, this
Bonferroni
is the most conservative. This will probably come next. Then this one and this one. But I really don't want to put an absolute like this because if somehow you restrict your comparisons, let's say we had 6 possible things here, all in this example of 4 groups, all 6 are an exhaustive list of possible multiple comparisons. Let's say you threw it out on a biological basis, 4 of them, only 2 or 3 of them you threw out, only 3 of them are you making this paper. That may become then roughly the same conservative nature as Newman-Cool's. Because Newman-Cool's, you don't have that option. It always begins from highest to lowest and then it goes down. It will do as many as that. So you see, it depends on what will happen. Generally, when I say that this is the most conservative, is when given number of groups, you do all possible multiple comparisons. Under those conditions, what I'm telling you is correct. But if you throw out some a priori, then sometimes the rank ordering may differ. And this one I threw out is this is actually I like it a lot. If your experimental design is such that biologically all you're interested is changes from a reference group. That's it. Usually control with perturbation. Then this Dunnett test is really good. It's exactly the same as Newman-Cool's, but it says I'm interested only, this is my reference group. It doesn't have to be the smallest one, but it's some reference group. And I'm looking for these 3, my perturbation groups, only with respect to reference, like wild type versus mutated, or whatever.
So then the denominator always remains the same as well?
Yes, this one here, it's very similar, and in the spirit is Newman-Cool's, but it really doesn't do all these range things.
So the denominator in this case,
you
span 4?
I have to look it up exactly what the it's not identical, but it's a kind of. So what I'm saying is that, let's say this was rank order, but this is your reference group. So one mutation fell the other this way, and the other this other. So this is the reference group, let's say. So it'll only do this, and this comparison. So it doesn't have to be rank order. So you just do. I have to look it up exactly what's inside, but as I remember, it is very similar to Newman-Cool's concept, using similar kind of analysis, same key type of thing. But I have to remember exactly how it does mean spanning in a concept, because mean spanning concept here is after organizing them in a rank order sense. So I don't remember that clearly. But the Dunnett test is really good. It's very similar in concept with Tukey or Newman-Cool's, but it's restricted to a reference group. And in biology, many times that kind of a structure occurs, because all you're interested is in reference group or control, wild type, whatever it is, and you want to compare that to a perturbed group.
Okay, point to be noted.
you have
To
you have
analyze
this.
your data.
Well, give me an example.
Analyze your data.
What's the structure? Just describe the structure of your experiment.
So I have a control group and then varying amount of mutations on a gas protein.
Various amount of mutations.
Yeah, so like that's what we're talking about. So the fast.
That as well as if you mutate one family protein versus the other family protein, all we are interested in whether it has any effect on motility.
Yeah.
So for example, the VASP has 3 members.
Yes.
So he's either knocking down VASP or either knocking down MENA or he's doing double knockdown.
Yes.
So if your interest is only studying whether one family member or 2 family member is slowing down the motility, your reference point is the control group.
Yes.
Outside. So in that case, probably done it would be.
Yeah, right. But in that particular case, would you be also interested in when you do double knockout of MENA, does that have an additional bump? Then you won't do that, right? If you want to answer that question, did it add to the the change,
Right.
or was it individually? So then you would not restrict yourself to the reference, right? Then you would be wanting to know double knockout versus single knockout.
Right.
Yeah.
So it's all depends, So basically, this is sort of. Just to summarize, then ANOVA basically, when you do multiple groups, means you're comparing means. It's a 2-step process. First step is all data together, just one answer comes, F value. If that does not come out significant, you're not allowed to go any further. You can't go fishing for differences. If that comes out significant, then you can do multiple comparisons. You decide what's relevant to you. All possible comparisons or some select comparisons. And so these are some of the all possible comparisons. I will choose either Newman-Cool's or Tukey, one of the two. That's what I would choose. All possible comparisons.
What did you use?
Tukey.